Today we will discuss Einstein's explanation of the photoelectric effect. First, we will take a look at the observations of the photoelectric effect made by various experiments, and then we will discuss why the classical wave theory fails to explain this new phenomena, and how Einstein's quantum theory of light was consistent with the observations. So what is the photoelectric effect? Well, it is when a metal surface is exposed to electromagnetic radiation, which causes electrons to be released. Well, 15 years after it was first discovered by Heinrich Hertz in 1887, Philipp von Leonard described the properties of the photoelectric effect. We can put Leonard's observations into four main points. Firstly, that electrons were immediately released once light hit the metal. Secondly, that as the intensity of light increased, the number of electrons increased. Thirdly, the kinetic energy of these released electrons was independent of intensity and dependent on the frequency of light. And finally, that there was a cutoff frequency under which no photon would be able to eject an electron. However, the dominant theory of light at that time, the wave model, was only consistent with 1 out of 4 of Leonard's experimental observations, and most importantly, it predicted that the kinetic energy of electrons was dependent on the intensity of light rather than the frequency of light. Seeing these obvious problems and the disconnect between the theory and the experiment, in 1905, Einstein published a paper where he took Planck's idea of quanta and used them to explain the photoelectric effect. Einstein's revolutionary model conceived light as particles instead of waves, stating that the energy of light is not evenly spread out, but concentrated in packets of energy which Einstein called photons, and each photon's energy is determined by the equation E equals hf, where h is Planck's constant and f is frequency. Thus all photons with the same frequency have the same energy. The intensity of light is proportional to the number of photons. Therefore, using his new model, treating light as discrete quantities of energy, he was able to describe the photoelectric effect in terms of the individual interaction between one photon and one electron, almost like any other collision of objects. Einstein's model predicted that the kinetic energy of the electron emitted was related to the frequency of the photon by the linear equation E equals hf minus w, where w is the work function or energy required to overcome the binding energy of the electron to the atom. Thus, if a photon's energy exceeds this threshold, then the electron it hits will be released, while if the energy is less than this threshold, then the electron would not be moved at all. This is called the all or none principle, which is where a photon can give up all or none of its energy, but not part of it. Einstein's linear equation was experimentally proven later by Robert Millikan, who devised an experiment where various frequencies of light were shone on a metal. His experiment produced a graph of results which validated Einstein's earlier predictions. Therefore, returning to our initial observations, Einstein's model predicts that there should be no time delay, as the collision will instantly either cause the electron to be released or not. And as the intensity of light increases, the number of photons increases, and thus the number of electrons which are hit and therefore emitted increases. And as the frequency of the photons increases over the threshold, the kinetic energy of the electrons emitted will continue to increase. Therefore, Einstein's theory of the particle nature of light fully explained all the observations of the photoelectric effect, and gave us a superior understanding of light beyond the classical wave theory, showing that light had both particle and wave properties.